here. Okay, so a lot of people missed Wednesday's class. I'm not surprised, but I just want to kind of cover a few topics. We looked at cross-validation and kind of the idea of cross-validation is that you might have a data set, and in k-fold cross-validation, so if we do 5-fold cross-validation, we split the data randomly into kind of different segments, and in 5-fold, 20% will be reserved as kind of a validation or test set, and then the other 80% are used to train the data. And scikit-learn includes something called cross-val score, and what that does is it looks at you fit your data to the training portion, and then and you'll have a resulting model based on the training portion, and we see how well does that model perform versus the validation set. Okay, so let's say this is my model. Normally, if I wanted to fit a linear regression model, I would just look at all the points and fit a linear regression model, and we would get something like this 0.5372, which is just our r-squared value. Okay, so if we did kind of the correlation coefficient, we would get an r-squared value of 0.5372, which basically says how much of the variation in y is explained by the variation in the model. Okay, versus the empty model or null model, having no model, would say we would just predict the mean of y for every single value. Okay. To do cross-validation, all you would do is, you would create kind of these cross-validation splits, okay? And you would just feed it into model.selection cross-val score, and you look at the model that you're trying to fit. In our case, a linear model. So to fit the linear model, we just say we want linear regression. We're going to fit it based on our x and y data, and this is what it gets. Okay, and these are the cross-val scores that we get. We actually get a negative value, something close to 0, and then a 0.49 and a 0.756 and a 0.65 and a 0.412. Okay, how can you get a negative value? That seems a little bit strange. Okay, I wrote this loop here, and basically this is our first fold. Okay, the light blue dots. So we took all the data points here, okay, and we said 80% of them will be our training data, and the remaining 20%, which were randomly selected, is our test data. Okay, so we fit this red line according to the light blue dots. Okay, we fit the red line according to the light blue dots, and we want to know what is this performance, what is the performance of this red line on the validation set. Okay, and so the validation set are the green dots here. Okay, if we fit no model at all, we would just predict the mean for every dot in the green in our validation set. Okay, and the variance of our data would be kind of the average squared distance from each green dot from the green line. Okay, that's the idea of having no model. In our case, though, we fit the red line, and we want to know, okay, well, how much error do we have between the green dot and the red line? And it turns out, if you sum up the squared differences, okay, which is what I did here, okay, the variation of just the green dots is our kind of our mean squared error. And then here I just say, what's the difference between, our predicted value, the red line, and the actual green dot, our actual value, and we square that. What's that square distance? Take the average. It turns out that average square distance is larger than if we just took the variance, where we were just predicting the mean for everyone. Okay, so this red line actually performs worse than just predicting the mean for everybody. And so in that case, if we just say, the mean squared error minus the mean squared regression divided by mean squared error, that's going to be kind of our reduction. And in this case, we have a negative reduction in the mean squares. Okay, so that's how we get a negative thing. Over here, the red line outperforms the green line. Okay, so when you use the green line to make predictions, you get a mean squared error or variance of 48.7. When you use the red line to make predictions on the green line, you only get 24.7 for the mean squared error. So you do have a reduction of about 50%, 49% there. Okay, and then we can look at all 5 folds. This one we have a significant reduction. So the red line actually predicts the green dots very well. Okay, and so we have a 75% reduction in the mean squared errors. Okay, and we can do this for all of these things. And overall, we just kind of average when you do cross-validation. Generally, you find the different cross-validation scores, and then you might just take the mean of all of them. Okay, and this kind of just to kind of illustrate the difference the bias variance trade-off is that you can fit more complicated models. Here we're fitting a quadratic model, saying does that do a better job? Okay, and of course as you add more terms to your model, you can fit your data even better. Okay, the question is, will this generalize for unseen cases? Okay, and so here we do the same thing. We train on the blue dots, and we see how much error do we have on the green dots. Okay, and when we do that, so we can see the curves are just ever so slightly different because the blue dots we use to train the line is different. It's more pronounced with, so I'm hitting higher order polynomials. Okay, so here I'm going to fit models of degree 4, and so we train a 4th order polynomial on these blue dots, and depending on the random selection of blue dots, that 4th order polynomial might take on vastly different shapes. Okay, when we fit a 4th order polynomial to randomly selected blue dots, we get different shapes. And so for something like this, okay, this red line fits the blue dots, but we can see it doesn't do a great job on predicting the green dots that we've kept in our test case. Okay, and so that gets reported in the reduction as far as the cross-validation score. And so when you fit the 5th order polynomial, the average cross-validation score is only around 22%. Okay, and then with 5th order polynomials, you get even worse, higher variation. Okay, we fit the blue dot here. Okay, and this does a terrible job because out here with a 5th order polynomial, it's predicting something out here, but the true dot's out here, and we're predicting something way down here, but the true dot's up here. And so our the mean squares for the regression model that we fit is really terrible, and we're getting a reduction of negative 1.86, okay, which means we're doing far worse than just predicting the average for everybody. Okay, same kind of deal here, just really bad performance with a fifth order polynomial. Our cross-validation score is quite bad. Okay, and so anyway, that's kind of the notion of cross-validation, is that you can we split up the data into these training and validation sets, and then we just compare. We fit a model on the training set, and we see how does it perform on the validation set. Okay, and so you can kind of look through this. I wrote out the whole code here, and then I just turned it into a function. Okay, because kind of following my rule of instead of copying and pasting multiple times, it's better to just write a function, and then you can call the function again and again. And so once I wrote the function, then fitting it for cubic fits and fourth order and fifth order fits became quite easy. Just a small chunk of code there. Okay, and that was powered by using the function CV for shuffle split. Here I've got basically the same thing, but this time we're going. I'm doing some classification data, and so we're going to look at the iris data set where we've got petal width and sepal width and stuff like that, and we want to use that to classify what kind of data we have. So the function I'm going to take a look at today is train test split, which is also part of scikit-learn's model selection. Okay, and again, scikit-learn operates from a different philosophy than your traditional R stats models, or not stats models, your traditional R methods for fitting a model, in that rather than looking at p-values and stuff, our model selection is very strongly powered by cross-validation. We just say, does this generalize to unseen data well or not? And if it does, that's how we say, okay, this is going to be an okay model to use. Hang on, let me. So here, just to kind of demonstrate how this works, I'm creating. I have 3 arrays: an X, which is a 5x2 array, okay, and then we've got Y and Z. And Y and Z are kind of like what kind of the output or the prediction variable. And so you can have, for Y I have a numeric thing, and then for Z I have a categorical thing. Okay, so I've got, and so when you call train test split, you can give it an array, and you give it some kind of test size. And you set your C to random state, and when you do that, it says, okay, for the training cases we're going to use rows 4, 0, 3, and 5, and then so for the test cases we've got the remaining ones 1 and 2, and then you can do the same thing with you can call it on Y, and if you use the same random state, it's going to match it up appropriately. Okay, so it says the value you're trying to predict is 4, 0, 3, 5, and for the test cases it's 2 and 1. Okay, and that's because we said test size is 1/3. I mean, you can specify it and say your test size is 1/2 or whatever you want it to be, and it will generally work. Of course, it probably makes more sense to call it on your feature matrix X and your predictor outputs Y. Okay, so you'll give it a 2-dimensional array X and your one-dimensional array Y, and then when you call train test split, it's going to return a tuple of length 4 that you can then unpack into X train, X test, Y train, and Y test. Okay, and so this is basically doing the exact same thing we did above, but just all in one step. Okay, so we get, for the training X, we have 4, 0, 3, 5, and rows 2 and 1, and then for the test Y, training Y and test Y, we have 4, 0, 3, 5, and then 2 and 1. Okay, so that can be done all in one step there. Same thing with a categorical variable, okay? Except with a categorical variable, you probably want to use the option stratify on the categorical variable, okay? And so our variable Z has 3 yeses and 3 nos, and by saying my test size is going to be 1 and 3, okay, even though I'm using the same random state as before, we pick up different rows, and that kind of ensures that in my training case I've got 2 yeses and 2 nos, and in my test case I have a 1 yes and 1 no. Okay, you can use stratify equals Z. If we didn't specify stratify equals Z, and I did this, then there's no guarantee. So because I'm using the same random state, it's using rows 4, 0, 3, 5, same as before, okay? But then what happens is that in my test case, I have no yeses, and I just have no's, all right? And so this is probably, as far as training goes, this might not be ideal because I have 3 yeses and 1 no, where in my test cases I have 2 no's, all right? And so that's probably undesirable as far as categorical training. Okay, so you can use your train test split this way, stratify Z. Okay. All right, so here I'm going to load up our iris data set, which comes in as a bunch, okay, which is basically like a dictionary, but you can hold different types of data, all right? And so I think you guys are all familiar with the iris data set, which is a very famous data set for classification, because we've got 3 classes of flowers or irises that we're trying to figure out, 3 species, and then for each of them we have 4 numeric variables that we're looking at: sepal length, sepal width, petal length, and petal width. And so this is all stored in iris.data. This is our feature matrix, okay? And then the target is just a one-dimensional array, and this is categorical variables, 0, 1, or 2, and they correspond to the labels Setosa, versicolor, and virginica, okay? And then you can even read on the description of the iris data set, and this is interesting. It says the data set is taken from Fisher's paper, which is the exact same as it is in R, but the UCI machine learning repository has 2 mistaken data points, so just be warned there, okay? And then so we can do a train test split on our feature matrix iris.data and our output variable iris.target, and then here we're going to say we want 20% of our cases to be in our test case. We'll specify a random state, and then we're going to stratify on the iris target to kind of ensure our categorical variables are represented appropriately, okay? And so if I look at this and I just say, bin count for Y test, we have 10 of each category, which is what we want, right? So we have 150 observations total. We're going to have 20% or 30 of them in our test case, and we're going to have 10 of each version there, okay, or of each species. All right, we can just doing some exploratory visualization. I'm going to use Seaborn and just do a pair plot, and here we're just looking. Did this not? Yeah? Okay. T.show. Is that gonna work? No. Ignore print SNS pair plot. Okay, there we go. Let me. Okay, it's still doing it. Okay, so here's our pair plot, and looks like this. Can I do all right, so we want to do this. All right, so we can fit like a k nearest neighbors classifier, and that just comes from sklearn.neighbors, k-neighbors classifier. You can learn This is just one of the classification methods. There's other ones. So I'm looking at the k-neighbors classifier and then the Gaussian naive Bayes classifier. Okay. And again, more examples and stuff in the documentation. All right, so what we'll do is I'm going to just initialize a model. All right, and when I do that, it just says, all right, we're going to do, this is what we've got. All right, we're going to use number of neighbors 5. I'm going to say, all right, let's fit this on our training data using xtrain and ytrain. And then based on this, we will make predictions on x-test, and we'll compare that to y-test, all right? So we can see this is what it's predicting based on the x-test, and this is the actual values in y-test, and we can see they're mostly exactly the same, except for right here, we predicted 1 and the true value is 2, and I think everything else is correct, okay? We can run a confusion matrix, which just says how many are misclassified, okay? And it says basically when the true answer was 0, it classified 0 10 times, and it misclassified them 0 times. When the true answer was 1, it classified it as 1 10 times. And when the true answer was 2, maybe I'll write this, okay? True answer is in rows, and the prediction is in the column, okay? And so we see that when the true answer is 2, the prediction was 1 one time, okay? All right, so that's what we get. So the true answer was 2, okay, in the bottom row, and the prediction was made to be 1, okay? So no errors would be a diagonal matrix. Okay, so we've made one error. Okay, so here we can say, all right, what if I'm going to just change my my model. Instead of using 5 nearest neighbors, what if I only used 1 nearest neighbor? Okay, and so here, maybe I should call this KNN1. Okay, so KNN1, I'm going to just use nearest neighbors 1. I'm going to fit it on my training data, and we're going to run the confusion matrix on our test data. Okay, and we get same performance, and then we'll call this one KNN25. All right, and then so with slightly worse performance with 25 nearest neighbors. Okay, so here, when we used 25 of our nearest neighbors to make the decision, we made 2 errors, okay? We have 2 errors. The true value is 2, and we predicted 1 twice. Okay. This, you can run something called grid search cross-validation, okay? And here it says, so I could say, you know what if I want to just try nearest neighbors 1, nearest neighbors 2, nearest neighbors 3, nearest neighbors 4, all the way up through nearest neighbors 50 to just kind of see which parameter is going to be the best one, right? So here, let me just, all right. What if I want to test out a bunch of different nearest neighbor values. Okay, so we can try a KNN with one nearest neighbor, a KNN with 2 neighbors, KNN with 3 neighbors, etc. Okay, so rather than having to do this over and over and over again, we can do what's called a grid search. Okay, so rather than manually fitting like 50 different models, we can have Python automatically fit all 50 models. Okay, 50 models for us using grid search. Grid search CV. Okay, and so grid search CV will try a bunch of different models. Okay, and you can vary more than one parameter. Although for us, we're just varying the number of neighbors. So it'll try a bunch of different models, and we'll report back the model score. Okay, the cross-validation model score here. And so, so we say, the grid that we're going to search is we specify, which which parameter are you going to mess with. Okay, so as far as the KNeighbors classifier, up here we would change the parameter nNeighbors, right? So that's what we specify here. Okay, so we make a dictionary called parameter grid, and the keyword will be the argument that goes into the model. So because when we use a KNeighbors classifier, we're changing nNeighbors to 25. Here we're going to say change nNeighbors to all the values from 1 through, I guess, 49. Okay, and then we say, all right, we're going to define KNeighbors classifier as KNN, and then KNN CV will be our cross-validation grid search. So we say we're going to do grid search CV. We're going to fit the KNN model, and as far as the arguments that we're going to use, we're going to have it search across the parameter grid. Okay. Now, if there was another argument in KNN, you could also specify that here, but now you have like, I don't know, geometrically more values to search over, right? So here we got 49 nNeighbors values to search for, and then if there was something else, like let's say where there was a bandwidth parameter or something and you want to search across 10 values, now rather than fitting 49 models, you're fitting 490 models, okay? And then if you had another 10 model, so if the more things you add, it grows exponentially, and your computational time will also grow likewise. Okay, but anyway, we're going to set search on parameter grid here, and then we'll do a 5-fold cross-validation. Okay, and in this case, because it's cross-validation, we're just using the training data, not even checking it against the test data. So it takes their training data and then further splits that into a training and validation set. Okay. All right, so we call KNN cross-validation.fit. So this part looks almost exactly the same here, and it takes a while to search because it's searched across all of these parameter values, 1 through 49. Okay, and then we can say, all right, what was the best parameters? It says nearest neighbors 13 kind of gave us our best score, and then we still get the exact same I guess matrix here, and the best score here, this just uses an accuracy or accuracy score, which may not be the best metric. Okay, and if you look up k-nearest neighbors, so every model that you can fit in sklearn, it's going to have a score thing, okay? A score method. And in this case, it means returns the mean accuracy on the given test data and labels, okay? Which may or may not be the best. It's kind of like a default score, and there is a way to change the way you want to do the scoring, but I forget how to do it right now. So anyway, but it says we're going to do this, so then we can fit k nearest neighbors with 13 nearest neighbors, and then we fit this, and we get on our training data, we get 118 correct classifications versus 120, right? And we can see, you know, I don't know, if I tried something else. So if I used 12 nearest neighbors, we get worse performance, okay? We have four mistakes in our training data. With 13 nearest neighbors, I only have 2 mistakes on our training data. With 14 nearest neighbors, I have 3 mistakes, okay? And then we can kind of, you know, you can just kind of go through and see, like, manually how many mistakes we're making. And so the grid search does indeed kind of return the best score it gets on the training data only, okay? Using cross-validation. And then based on that, we can see, you know, if it makes any mistakes on the test data, we still get the kind of the same performance on the test data where we've made one thing. So, you know, unfortunately, it's not any better than what we had before, but it does produce kind of the minimum number of mistakes as far as our training data goes. All right, so the grid search is kind of handy in case, like, you want to fit a bunch of different model parameters to try to figure out which, you know, what n or what k to use for your k nearest neighbors, right? And so so here, no longer doing a grid search, we're just going to fit k nearest neighbors with 13 things. You can look at the cross-validation score, okay? And so the cross-validation score, again, takes our data set, splits it up into kind of five chunks, and it uses each one for a validation set, and says, I don't know what this is, but you know, in 3 out of the 5, it made no errors, and then in 2 of the 5, it made 1 error, and we get this. Okay. I think I accidentally duplicated this. All right, but anyway, this is it's a handy thing, this grid search CV, and allows you to kind of fit different things. Let me let me do Gaussian naive Bayes if I've got. So we'll do oops. Let me try. Oops. Okay. Gaussian naive Bayes. All right. So we'll try. I'll call this NB class. Will be Gaussian naive Bayes. And what are my options for specifying? I guess we'll just try this Gaussian naive Bayes, and then we'll do NB classifier dot fit on x underscore train, y underscore train. And then we'll do NB class dot predict on x underscore test. Oops. And let's print out our confusion matrix. Y test on NB class test. Yeah, I guess the way our data split up, it's just maybe there's whatever this one observation is. It's giving all of our models a hard time here. Let me see if we can do. Let me see, naive Bayes. Can I do cross-validation score on this naive Bayes classifier? And our performance isn't that great. I guess well, I mean, it's fine, but the you know, our average cross-validation score for 5-fold cross-validation on the training data only is 0.95, which is a little bit lower than using a 13 neighbors classifier. Okay, but you know, to figure out the 13 neighbors classifier, you know, we had to do a grid search across all those values. Whereas the naive Bayes, let me see, what options can I mess with? Yeah, I guess we can change the priors, but I think the regular prior is it's gonna do. I don't know. How do I? Priors none. Specify the priors are not adjusted according to the data. Okay, so yeah, we so normally we just fit a Gaussian prior, and we center them according to the mean and the variance that we observe in our data. Okay, but if for some reason we had prior beliefs about where the mean and the variance is for each classification, then we can specify that, okay, in our Gaussian naive Bayes. So, for example, in the training, as far as fitting the Gaussian model, it's going to look at the average petal length of species Setosa, and then it will also look at the average sepal length or whatever for species Virginica, and it's going to use that as the mean. But then, you know, you can specify the priors. But I guess, you know, with the naive Bayes, it's kind of an out-of-box thing without a whole bunch of parameters to mess with. So maybe it wasn't the. I can't really do a grid search cross-validation for that. But anyway, just some quick examples here for I don't know what kind of models you guys are fitting for your data yet, but these are just some tools that you can use as far as trying to find the best model. And you know, I have office hours, and so if you guys have questions on how you should look at your data and some ideas, I'm more than happy to kind of just be a sounding board for you to kind of bounce ideas off of, or ask for some advice there. I'd much rather you guys ask questions now than I don't know, after you submit it and you know, and see what you've got. Okay. All right. I guess we'll end here for now. Are there? I'm eventually going to get to SQL, okay? Because I know that was like a topic you guys want, but it's like not super relevant for your immediate project now. So I kind of want to give you stuff regarding the project, and then the SQL stuff will probably come in 10th week. And honestly, we don't need even more than like 2 lectures on it. Okay, it's an easy topic. If you know how to use dplyr, then SQL's a very natural transition. So we'll get there. Okay, but let me know if there's certain things you want me to kind of investigate or cover in lecture as well. Okay, we'll see you guys on Wednesday.